Okay, in section 4.4, we're going to continue our discussion of vector spaces, focusing on coordinate systems. Now, coordinate systems is something we've talked about. So this first part, we'll look at some coordinate type systems that we've actually worked with already. And then we'll expand that into some of our new vector spaces that we can treat as similar to those spaces that we're dealing with. So if I have a basis B, so given a basis B, get my camera to cooperate here. All right, given a basis B, and we'll name the vectors in that basis, B1, B2, all the way out to Bn. So I have n such vectors in my basis B for vector space V. Okay, so I have my basis B for vector space V, B1 through Bn. Okay, remember that it's a basis, so this tells us that these vectors are independent and span the entire space V. Okay, so since I have independent vectors, I know that V is n-dimensional, for example, and that if I set the equation perhaps equals 0, it would have only the trivial solution, things like that. Okay, so I have a basis B and for a vector space V. So for each x that's inside of V, so each x that's in V, there exists a unique, so unique, just one, set of scalars. Remember, scalars are just numbers. Okay, and those scalars are going to be C1, C2, all the way through Cn, such that I have just one linear independence relationship. Okay, I have that x, remember x is a vector here. Okay, it's a vector space, so the elements of it are vectors, such that x is equal to C1, B1. Remember, B's are vectors and C's are scalars. Okay, C2, B2, and that continues all the way to Cn, Bn. Okay, so there's only one way to represent this, and that way to represent it is exactly our coordinates. Okay, just as we talked about before. Okay, so the scalars form the coordinates or coordinate vector for x. Okay, and it's the coordinate vector in Rn. Okay, because I have n such scalars. Okay, so then our coordinate vector x is equal to each of these c's, C1, C2, C, all the way through Cn. Okay, again, we use that matrix notation to represent coordinate vector, and then we need to put it with respect to what basis. In this case, it's basis B. So your basis goes here in the lower left. Okay? All right, so if I have a basis B, let's make a nice simple basis. So B is equal to the following two vectors. Okay? That is 3, 1 and 6, -1. Okay, so this is clearly a basis for R2. Okay, because I have two vectors, they're clearly independent, they're not multiples of each other. I have two coordinates involved. Okay, so I know that those two vectors span all of R2, so that forms a basis for R2. Okay, if I have a coordinate vector x in terms of B that's equal to 2, -1, our question is, what is x? I remember x is a vector. Okay. All right. So I know I have this equation, right? I have this linear combination equation. Okay. This coordinate vector then corresponds to those weights. Okay. So I know that x is going to be equal to 2 times the first matrix vector, or the first basis vector, plus -1, because -1 is my value here in the coordinate vector, times B2, my second basis vector. Okay, so let's look at what that is. That's 2 times 3, 1. 3, 1, my first basis vector, minus, because it's -1, and this is 6, -1. Okay, so I add those together. So I know then that x is equal to 2 times 3 is 6 minus 6. X is 0. 2 times 1 is 2. Negative and negative is going to make a positive 1, so I get 0, 3. Okay, so 0, 3 is my vector x, given that basis and that coordinate vector. Okay, you can think about those grids we had. I'm going out 2 along the first vector, then minus 1 along the second vector. That's going to get me to 0, 3. Okay, now most spaces, I won't say every space, but the large majority of spaces have more than one basis. Okay, if you have the 0 vector space, then maybe not. But in general, there's more than one way to represent this basis. So we'll have what's called cursive E here, which is the standard basis. Okay, and we're familiar with the standard basis because it looks like the identity. Okay, 0, 1, 1, 0. Okay, so this is the standard basis for R2. Okay, so sometimes you would see it written as E2 to correspond that it is referring to R2. In general, we can infer that from what the vectors look like. Okay? I know what these vectors look like, so this 2 isn't really necessary. Okay, so if I take x, but now instead of being in terms of b, I'm in terms of e. Okay, well, I have no copies of this first coordinate. So in terms of the basis vectors, the standard basis, the coordinate vector is going to be exactly the vector. That is the importance of the standard basis. That's how we normally coordinatize our Cartesian plane, right? We count horizontally along the x-axis and vertically up the y-axis, okay? We don't usually count on those slants, okay? But we can, and we can go back and forth between the two, okay? All right, so if I have this basis vector E here, in terms of E, I have this coordinate vector, 3, 0, 0, 3. And I want to figure out what that coordinate vector would be in terms of my new basis. Okay, I can use those corresponding vectors to find that basis or to find that new coordinate. Okay, so if I'm given these basis vectors here, I can think of these as a matrix. Okay, so imagine this is a matrix A. Okay, so A is going to be this matrix 3, 1, and 6, negative 1. Okay. And now I know that if I were to take my vector x, okay, based on what we did previously, my vector x 0, 3 here, okay, and if I were to augment this matrix with 0, 3, okay, so I've augmented that, and I were to row reduce this, okay, that would produce my coordinate vector, okay, because that's how we determined that coordinate vector in chapter 2. Okay, we used that coordinate system to help us figure that out. So if I row reduce that, okay, just to check here, okay, so I'm going to plug in that matrix. Okay, so my 2 by 3 matrix here, 3, 6, 0, 1, negative 1, 3. Okay, so that 2 by 3 matrix, I'm going to quit, go back to the main screen. I'm going to do the reduced row echelon form of that matrix. You see I get 2, negative 1. Okay, because that's how we found a coordinate vector before. Okay, and 2, negative 1, remember, was our coordinate vector that we started with here. Okay, so what that means is this is analogous to using AX is equal to the actual vector. So let's actually call it AY just to use, just to be careful. Okay, AY is equal to X. Okay, so this matrix then, if I multiply it by my unknown Y vector here, okay, that unknown Y vector, right, was the coordinate vector. Okay, so let's use the coordinate vector in place of it. I should get X. So my matrix A here is called the change of basis matrix. Okay, and we can actually do this to go between any two bases. It only works this nicely when you're going to the standard basis. But this matrix A, you notice, is just the basis vectors. Those columns I could just write down as the basis vectors. Okay, and that works whether you're in R2, R3, etc. Okay, so we're going to look at some more examples here and expand our horizons into higher order spaces, but it will work for any space. Okay. All right, so next let's make a basis that's in a three-dimensional system. So I've got a basis B here. Okay, my basis B is equal to the following three vectors. Okay, 2, 1, 1, -1, 3, 1, and then the third one is going to be 1, 0, 1. Okay, my space H is a vector space with basis B. Okay, so if I look at these three vectors here, they're a basis. So if they're a basis, they must be independent. Okay, so basis means they're independent. If they're independent, then I have three of them, three independent vectors that are in R3 will span all of R3. So H is actually equal to R3. Okay, I get the whole space. So that means if I pick any vector, I should be able to find its coordinate vector, or if I know its coordinate vector, I should be able to work backwards. Okay, so we're going to find a coordinate vector X in terms of basis B if X is equal to the following vector, 9, -3, 2. Okay, so what we're looking for then is we're looking for C1, B1 plus C2, B2. Remember, my B1s here are my basis vectors B plus C3, B3 is equal to X. Okay, where B1, B2, B3, and X are all vectors. Okay, so be careful to distinguish there between the vectors and the scalars. Okay, so as I look at this is a vector equation. How do I solve a vector equation? I solve a vector equation using an augmented matrix. 2, 1, 1, -1, 3, 1, 1, 0, 1. Augment that with my x vector, 9, -3, and 2. Okay, we're going to go to our matrix now. We're going to plug in a 3x4 matrix. Okay, 3x4 matrix. That's equal to 2, -1, 1, 9 for the last one. 1, 3, 0, -3, 1, 1, 1, and 2. Okay, and I'm going to row reduce that matrix. Again, matrix, go over to math, RREF, reduced row echelon form of matrix A. Okay, I get 3, -2, 1. So this is X1, which in this case is actually C1. Okay, we're using C1 instead of X1. But I get 3, -2, 1. So my coordinate vector, this row reduces first. We know it's going to row reduce to the identity because those vectors are independent. Okay, these three vectors that I start with here are independent because they are part of a basis. Okay, so 3, -2, 1 then. So what that reduces to, which means that my coordinate vector X in terms of the basis is equal to 3, -2, 1. Okay. Now, I also know because of this, right, this was solving AX equal, I don't want to say X, sorry, AY is equal to X. Okay, that's what this matrix equation solves. Okay, I don't want to use X because I'm using X as my vector here. So it solves that system. You know, normally we've written AX equals B. Okay, but I don't want to use B because those are basis vectors, so I used X. Then since I used X there, I need to use something different on the left. So AY equals X. Okay, and the way we solve that, right, is by using systems of equations, row reduction, etc. Okay, and this also means that I can solve this using an inverse. Okay, so what is A? A is just the basis vectors. Okay, that means if I put this coordinate vector in here and I do A times this coordinate vector I found, I get out my original vector X. Okay, so remember that X itself is equal to the coordinate vector with the standard basis, curly E. Okay, so A is the change of basis matrix, just using the vectors. Again, that only works if you're going to the standard basis. If you're going to any other type of basis, you can't use that. We actually will talk about that in a later section. But for now, we're just saying, okay, it's just that. Okay, so we're looking for that change of basis matrix. We can just use the values of the vectors, just use the vectors that are given. We need that, okay? I also can treat this as an equation, right? I could multiply A inverse on the left of both sides, and I would get that y is equal to A inverse x. So I could actually do A inverse x. Remember what x is. A has to have an inverse because these are independent vectors. Since they're independent vectors, they have an inverse. Remember, that is a invertible matrix theorem, okay? So you have several ways you can solve. You can use the inverse. You can use augmented, okay? You can use vector equation. You use matrix equation, okay? They all get you the same place, okay? Now, it's important when we're talking about coordinate vectors, occasionally we might write them as a transpose. So I might write this as 3, -2, 1, but then say it is transposed, okay? Because that row vector idea sometimes makes more sense. You think about how we write an ordered pair or an ordered triple when we do typical graphing. We tend to write them horizontally, okay? But if you're doing that, all we're doing, right, is we're taking 3 times the first basis vector, -2 times the second basis vector, and 1 times the third basis vector. So if you have this long setup of a problem that says, oh, this is a given coordinate, find the original, take your basis vectors, multiply them by their components, right? We know this equation has to be true and it has to be unique, okay? That was, remember, this first thing I said in the chapter, is that it has to be unique, okay? Now, both of my examples so far have used systems where I had the whole space. I had all of R3 or all of R2, okay? But we can still do coordinates even if that's not the case, okay? So we'll have a new basis B here. And this basis B is going to include 2 vectors that are in R4. So -2, 1, 0, 1. And then my second vector is going to be 3, 1, 1, 1. Okay, there's my basis vector. Now let's consider what the implications of that are, okay? This is just 2 vectors. They're clearly independent, okay? 1, because H is going to be a vector space. Same conditions I wrote last time. H is a vector space with basis B. Okay, H is a vector space with basis B. So given that I have a vector space with basis B, I know these are independent. I also know these are independent simply because they're not multiples of each other. Just 2 vectors, so I can just say, can I multiply this by anything to get there? No, I got zeros and ones, positive, negatives, all mixed up, okay? So this is really only 2 vectors. So this is a plane. So H is a plane in R4. H is a plane in R4. Okay, H is not in R2, even though there's only 2 dimensions. H is in R4. It's not even a subset. R2 is not a subset of R4. Okay. Okay. Well, if I have a coordinate vector that's equal to -1, 3. So notice I just have 2 coordinates in my coordinate vector because I only have 2 basis vectors. I can find x, right? I'm going to take -1, multiply it by the first basis vector. I'm going to add that to 3 times the second basis vector, 3, 1, 1, 1. Okay, so we multiply those out. I'm going to get +2 plus 9. I get 11. Okay, -1 times 1 is -1, plus 3 is going to be 2. 0 plus 3 is going to be 3. -1 plus 3 is going to be 2. So I get 11, 2, 3, 2. So this is my vector x when this is my coordinate vector. Okay? Now, remember I said we can have multiple bases for the same thing. Okay? So let's say I have another basis. Let's call this basis C. Well, this basis has 11, 2, 3, 2. For the first vector, and the second vector is going to be 1, -1, 2, and 0. Well, as I look at x here, x is clearly one of my basis vectors in this case. So the coordinate vector for x with respect to c has one copy of the first basis vector and no copies of the second basis vector, because I don't want to add or subtract anything to it. It's already the basis. Okay? So notice these two basis vectors are very different. Okay? But they both refer to the same space or the same point in a different space. Okay? These two planes are very likely not identical. They may be by coincidence. I didn't double check. It'd be very unusual though. These two planes are likely not identical, but they have a point that's the same in both of them. Okay? So they intersect in some form or fashion. Okay? So we can have points that are in two different bases or in the space created by different bases. Similarly, we can have things that are that correspond to the same point with two different bases. They're not going to have the same coordinate vector. I could also have a situation where I do have the same coordinate vector, but it's not the same space, not the same basis. Okay, I just take two different paths, so to speak, to get there. Okay. Now, this is also called the coordinate mapping. Okay, coordinate mapping. Right? When you hear the word mapping, that should invoke the idea of a linear transformation. Okay, so this takes vectors x and it sends them to their coordinate vectors. Okay, and it does that by multiplying by some matrix. It's like a linear transformation. Okay, all right, so we should have a pretty decent handle on using it when I'm just in R4 or R3, etc. But what if I'm in one of my new vector spaces that we just first talked about in chapter 4? Okay, what if I'm in P3? Okay, so let's take the space P3. Remember, that's all the polynomials with degree 3 or less. Okay, the standard basis for P3 looks like this. It has a vector 1. It's going to have one for t. It's going to have one for t squared and one for t cubed. Okay, so notice it has 4 basis vectors. So these have corresponding vectors that we could imagine in R4. Okay, R4 has a standard basis. And that standard basis looks like the identity vectors. So 1, 0, 0, 0. Our second one would be 0, 1, 0, 0. Okay, our third one right would be 0, 0, 1, 0. And our fourth one would be 0, 0, 0, 1. Okay, now the way I've written these right now, I'm going to place them in correspondence. So my 1 vector here corresponds to that first vector, t to the second one, t squared to the third, and t to the third to the last one. As long as you know what order you are thinking of them corresponding, you could actually do them in any order. You just have to be able to keep it straight. So most people would go in order, but you might go the other order, right? You might put t cubed at the top, then t squared, then t, then 1, okay? But the typical arrangement is to go 1 to the left, then t squared, then t cubed. Okay, so that you increase in powers as you go. Okay, that's the typical arrangement for that. Okay, but that's not the only basis, right? I could have a basis. Okay, so my space H is a subspace of P3 with basis B, and this basis B has the following vectors: 1 minus t squared, t minus t squared, and then the third one is t cubed. Okay? So these are in P3, okay? It's difficult to think about these in P3, although sometimes we can eyeball them, okay? So let's look at them instead by using their analogous vectors in R4. Okay, so I'm going to call this B star because it's not B, but it looks like B and it has the same structure as B. Okay, so I look here, I have 1 copy of 1, no t's, negative 1 t squared, and no t cubed. Okay, second vector has no copies of 1, 1t, negative 1t squared, and no t cubes. And then my third vector has no copies of anybody except for t cubed. Okay, so those are the corresponding vectors. Now, if I'm interested in finding the coordinate vector for, okay, so we're going to find x with respect to the basis b, so the coordinate vector for b, if x is equal to 2t cubed minus 3t squared plus 2t plus 1. Okay? Now, we can do some eyeballing of this matrix, of this setup, and we can start to figure some things out, right? I know I'm going to need 2 copies of this third vector because it's the only one with t cubed in it. Okay, but I've got some interactions between t squared and t. I could probably guess it out. Okay, for instance, I can match up the ones. Okay, so I can match up the ones there and find that as well. Okay, so what have I figured out so far? I know I need 2 copies of the third one. Okay, so I need 2 copies of the third one. So let's give these names. Let's call them B1, B2, and B3. Okay, so I need 2 copies of B3 for sure because I need that to match up to that 2t squared. Okay, I need 1 copy of the first one because it has the plus 1 involved. Okay, so 1 copy of B1. Now in the middle here, if I've got a copy of B1, I have negative t squared already. So negative t squared, okay? So I need 2 more of those. Well, if I do 2 more of those, I'm going to get 2t and negative 2t. So that actually will work here, okay? We actually could eyeball this matrix without too much difficulty, okay? That is going to be equal to x, okay? Check and add them up, right? 2 times t cubed is t cubed. 1 times this is going to give me 1 minus t squared, but then that's going to be added to 2t minus 2t squared. So 2t squared and negative 2t squared and negative t squared is going to give me negative 3t squared. And then I'm going to get 2t and 1. Okay, so my coordinate vector has 1 copy of B1 and 2 copies of B2 and B3. Okay, but it may not be so easy to just eyeball these. Okay, so we want to use our R4, our standard basis vectors here, our regular basis vectors that we're familiar with, to help us find that. Okay, so I've got my system here: 1, 0, negative 1, 0, 0, 1, negative 1, 0, and 0, 0, 0, 1. And I'm going to augment that with my vector here that's corresponding. So let's call this x star. Okay, x star has 1, 2t minus 3t squared and 2t cubed. Okay, so this is the corresponding vector in R4 that matches up with this vector in R3. So I can augment that onto my matrix, right? Before I put these in vector form, in R4 form, I couldn't easily write this type of equation down, okay? I really just had the one equation, but I can turn it into something that I can work with, okay? So as always, right, take you calculator, type in your matrix, make sure you get all the numbers in correctly. Okay, we're going to row reduce that matrix, and you can see on my calculator here, I got 1s along the diagonal with 1, 2, 2. And there is my coordinate vector 1, 2, 2. Okay, your coordinate vector only has 3 positions in it because you only have 3 basis vectors. Okay, anytime you can set up that situation, you can use that to your advantage. Okay, use what you know about R4 to turn a situation with a polynomial into something that's easier for us to deal with. Okay. So let's look at one from P2. Okay. So I'm going to have B. B is going to equal the following vectors: 1 plus 2t squared, 4 plus t plus 5t squared, and 3 plus 2t. Okay, so the question is B a basis for P2? Okay, now remember, P2 is all the polynomials of degree at most 2, which is analogous to R3. So the fact that I have 3 vectors means it's a possibility. So remember, P2 goes with R3. Okay, so R3, I know it's 3-dimensional. I need at least 3 vectors if it's going to be a basis. Okay, I've got my 3 vectors. I want to figure out if they're a basis. So I want to use my matrices notation to check if they're independent. Okay, so my first vector here is 1, 0, 2, because I have 1 copy of 1, no t, and 2t squared. Second one, I'm going to have 4, 1t, and 5t squared. Third one, I've got 3, 2t, and no copies of t squared. Okay, row operations. Do your row reduction on this. Okay, check and be careful. Make sure you get everything right. Okay. Let's do a couple of row operations just to refresh our memory in case it's been a while. I'm going to do -2 row 1 plus row 3 is going to replace row 3. Okay, so row 1 is unchanged. Row 2 is unchanged. My new row 3 is going to be 0. -2 and 4 is going to make 3. Sorry, -2 makes -8. -8 plus 5 is going to make -3. There we go. And then -2 times 3 is -6. -6 plus 0 is -6. Okay. Okay, so I go to my second pivot. I've already got a 1 here. I want to go below it. So 3 times row 2 plus row 3 is going to replace row 3. Okay. So I've got 1, 4, 3. I've got 0, 1, 2 because I didn't change anything about row 2. Now I've got 0 plus 0 is 0, 3 and -3 is 0, and 6 and -6 is 0. So what does this tell me? This tells me that this vector, this last one, is dependent, right? Dependent. So the corresponding vector here is already covered by these first two, okay? So B3, let's call it, is dependent. That means that B is not a basis. So we would not even consider writing coordinate systems for it because it is not a basis. Okay? So when you have questions that talk about these polynomial spaces, P2 and P3, you can always convert them to R3 or R4 or R5, whatever the corresponding space might be. Okay? You can always go to that. You can do your row operations, okay, and you can then make an observation about what the situation is, okay? All right, so coordinate vectors, right? We're using that linear combination property to write those coordinate vectors. We're looking for those scalars C. So we only talk about coordinate vectors when we have independent sets, okay? If you have a basis, you know you have an independent set. All right, so that's the end of section 4.4 on coordinate systems. Okay, 4.5 is going to look at the dimension of a vector space. Okay, the dimension of a vector space. And then we will continue from there into 4.6 as well. Okay, we also have that section to cover. Okay, and then after 4.5 and 4.6, we shift gears a little bit for chapter 5 and we talk about eigenvalues. Okay, again, make sure you're carefully taking care of your weekly assignments. Okay, make sure you're staying up to date. Again, there's some flexibility and some due dates. Okay, but if you fall behind, you're just going to make more work for yourself later down the line. Okay, so make sure you're on top of things. Make sure you're getting to all the checks for understanding and quizzes and tests as they come up. Okay, if you have any questions, please don't hesitate to send me an email. Okay, let me know how I can help. You can also visit office hours in the appropriate means. Again, if you need help with anything, please don't hesitate to contact me. I'll be happy to get with you. Okay, so I'll see you in the next video for 4.5 about dimension.